Today's topic is exceptions and error handling. And this is a major topic in actual programming. A lot of the time you would spend actually programming up a real project or a real system in industry would be devoted to error handling. A significant fraction of all the work, depending on the domain, is going to go into error handling and thinking out all the error cases and making sure they're handled gracefully. And as I say in the notes, it's certainly not the most fun part of the problem, but it's important. And so first of all, let's talk about what could go wrong. I mean, you have your program. It's kind of correct. What could possibly go wrong? Well, there's first of all, you give this thing to users or either end users who are typing at it or people who are using your library if you created some library for them, unexpected input. Okay, people are going to give basically any random input to your program, and your program has to do something reasonable with just about any input. Many of you found that out unexpectedly in some of our problem set tests for Func3 when we asked you to bracket a root which wasn't there. Okay, that was not us intentionally being clever and leading up into this. That was just me using Emacs to cut and paste when I shouldn't have. But it nonetheless brings up the point that you've got to be able to check that whatever assumptions that your program or library makes coming into it are really true. Okay, so, and the input could be incorrect in a couple ways. It could be syntactically incorrect, which means it might be just the wrong type, or it could be semantically incorrect. Also, this is related, but a little different. I/O errors. We're going to talk about I/O tomorrow, but this is a great source of exceptions where you have a program that's supposed to read some stuff from a file and write some stuff to a file, and all sorts of stuff can go wrong. The file could be not there. The file you're supposed to write into or read from could be not there. The file you're supposed to write to could be not creatable because you don't have permissions to create it. The network file system could hiccup in the middle of your writing, and so your attempts to read or write could fail. And all these things are going to generate errors, all of which you need to handle more or less gracefully. There's also internal processing. Errors. And maybe I'll lump system errors into this. Okay, the processing errors would be things like divide by 0, array out of bounds, when you try and access off the end of an array, and null pointer access. 2 C's. Actually, I'm going to give you another list of these because they're actually treated differently. Null pointer access is what happens when you declare an object variable, don't initialize it, or initialize it to null because you haven't don't know what's supposed to be there yet, forget to actually put something in there, and then send it off to a method that expects there to be an object there. So it'll get there, it'll find that there's nothing there, and it'll give you this complaint. These are really the main 3 types of processing errors that you will get. Also, sometimes method not found. Okay, you'll call them, try and call a non-existent method. This one seems to be handled by occasionally returning infinity or not a number in the latest system. System errors are things like you run out of memory, the Java runtime, where you just have runtime failure, general system crash, things like this. Things when the lowest level of stuff that you depend on for your program to work just fails on you. Okay? These things you can't really do too much about. And you can classify these as into 3 groups, and that'll map onto the Java classification. So I mentioned it. This one, these guys, as I say, are somebody else's fault, and there's nothing you can do about them because basically the whole computer is about to die on you. And these, on the other hand, are entirely your fault and should never happen. Okay? These are indicative of programming errors, and if you do thorough testing, these are indicative of pure bugs in the programming. Okay? You might have code, you might want to put code defensively somewhere to catch them just in case, but they should never happen, and they're indicative of bugs. These are, so these might fall into the category of errors. These are your true dealable exceptional conditions. All right? They're a little different from here in that they're not the programmer's fault. They're not the system's fault. They're essentially the user's fault. And those, but you have to be able to deal with them. So you have to be able to detect these anomalous conditions. And you have to be able to deal with them. So, in fact, there's 3 issues to go over. There's detection. How do you tell when one of these conditions is met? There is signaling, which is basically my term, which I kind of made up, but it refers to how to get the error from the place that you detect it to the place where you're going to do something about it. All right? Often you can detect the error way, way deep in one of these libraries, but you might want to handle it at some higher level because there's nothing you can do about it. And finally, there's once you've got it to some place where you're ready to deal with it, the question is, what can you do with it? Once you've got some anomalous input, what is it you're supposed to do to keep going? So let's deal with these in turn. For testing, detection, the main issue is where to do it. And your choices are kind of, you have a high-level choice and a low-level choice. You can either, say you're calling a library routine, which expects, say, our bracket root, which expects there to be a root between A and B, or in particular, it expects the function of A and the function of B to be of opposite signs, so that way we know there's a root. So there's 2 things that can happen. One, if you're writing the whole system yourself, you can test every time you are about to call bracket root, or the thing that calls bracket root, test to make sure that condition is true before you call bracket root, and then nothing's going to go wrong. So the first thing, actually, you have to do for each one of these things is decide on what that set of conditions is. Okay, what assumptions does this routine make about its input? Aside from being syntactically valid numbers, it really makes the assumption that f of A is a different sign than f of B. That guarantees there to be a root. It also makes the assumption, well, it may or may not make the assumption that A is less than B. That's an implementation dependent thing, but all these assumptions should be clear in the comments to your routine, And so you can either test before you call that routine, in which case the conditions for this routine are guaranteed to be met and everybody's happy, or you can test once you enter this routine. All right? Testing high level is good because it, you find out early what's wrong and can probably do something about it right away. Okay? Once you've passed it on to bracket root has the problem of once it figures out what's wrong, what does it do? Because its main function is just to compute this root. And we'll talk about that in a second. But another issue, though, on the other hand, is if this bracket root is a library that's going to be shared between multiple people. You've written this as kind of a service or a publicly available library, and your code isn't going to be the only thing using it. Well, then you've pretty much got to check, because you have no control over when it's going to be called or how it's going to be called. So basically, this guy not only has to publish what it expects its input to be, but also check that that's true of its input and be able to respond properly when that's not the case. Okay, so say we're doing this at low level. Say this is a public library that we're giving away, and we are checking for A and B being the same sign. So actually f of A, check for different sign. All right. What do we do if they're not the same sign? And a lot of you have ran into exactly this problem on the problem set. And again, there's a couple of choices. And they're all kind of legitimate choices. And how you do it is basically a matter of balancing external engineering factors. All right. So, okay, how do we signal to somebody outside of us? How do we signal to the program that called us that something went wrong? All right. One way is to return an error code. All right. This is a very common technique. You simply return some value, which is an error code. This has a lot of nice features about it. It uses the normal program flow mechanism. You call into the library, you get a return value. Everything is good. It is low overhead because it doesn't invoke any additional mechanisms that are in the, it doesn't involve any additional technology. So it's a very common and very pleasant way to do things. It does have one implementation problem in that it tends to use up that return value. All right? So you basically have to pick some return value to be error, and if you want to return some kind of further explanation of what type of error it was, you might have to use a range of values to implement errors. And the trouble is, how do you distinguish your error values from your legitimate values? All right? Sometimes when the return value of a method is an object type, or in other languages like C or C++, essentially a pointer type, which is the same as or analogous to a Java object reference type, people use the null value as an error code. Basically, if the method works fine, it actually returns you an object. If the method doesn't work, it returns you null. And then you just test on null before you proceed, and that's a convenient way. If you have functions or methods that return basic types or arrays, it gets a little more difficult, because then you have to pick some range. Like some people use things like a number or plus or minus infinity for double, though you could conceive of routines where even those values would make sense. Some people just picked arbitrary values of of an arbitrary big unlikely double to return, and just hope that that was never the legitimate answer. And granted, your odds are pretty good, but that's not the way really you would want to do things. So another advantage, I guess, a mixed blessing of this, okay? As I say, it's very efficient because you just propagate things in a return code. Once you start to do this through many levels of libraries, you find your code gets to be a bit cluttered, because every time you call any method, you then wrap that in an if statement where you're checking for the error code and then doing something, and if it's okay, you're proceeding. So basically your whole algorithm gets cluttered up to be this series of if statements on everything you do, checking for error codes. If you return error codes that way, you've got to do it, but the resulting code is less fun to write and certainly much messy to read. It obscures the underlying structure of the algorithm that you're trying to do, because it's, the code size is pretty much tripled by all of this error handling. Let's see, are there any other? Oh yes, there are. If you really want to use error codes and return a basic type or an array of something, there's another technique for doing it, and this is pretty standard, is to make the decision up front that, okay, all of my routines in this library are only going to return an error code. Okay, so all of my signatures are going to look like, say I return integers as error codes. So for bracket root, it would look like int bracket root of double A, double B, double E, my error code. And now since I'm using up my return value to return an error code, and maybe this is, you have a special value that represents success, and another set range of values that represent various types of errors, how do I get out the actual root I computed? And the way you do that is to pass in some array or class that this guy will modify, and then you get it back and you look for it. For example, you could pass in here a double, call it answer. And what this guy would do is internally, once it computed that, put it in answer of 0. Once it computed it, it would put it in answer 0. So the caller of this guy would first check the error code to make sure it was success. If it was success, it would go and then check the value of this. Okay, it would go get the actual value out of the 0th element of that array, which you passed in. That means that the guy who calls this has to allocate an array with at least one space in it, pass it into this guy, and return this. It's not as elegant as you would like, but it does the trick. It's fast and efficient. It still has the problem that you have to check error codes on every time you call anything, but it works. And there are lots of real libraries that do this. As a matter of fact, I just spent the last 6 months writing a kind of multi-module system where the interfaces between the modules used exactly this kind of protocol for passing back. Every routine simply returned an error code, and when you wanted to get actual results into it, you had to pass an array into it, and it would fill in the array, and then you'd look in the array for the results.
The reason you use an array there is because it's by reference? So
yes, exactly. Exactly. It's by reference, so that the actual contents of the array are shared between the caller and the callee. So anything that works by reference, you can use to do this mechanism. In C, you can actually pass in a pointer to some variable where you want this guy to fill it in ugly languages like that. In Java, you can't do that, so you have to do something like this.
Well, what about returning an object instead of the instance approach, you return an object instead of an
That's another approach you can get away with in a object-oriented language. Say you have for each routine, you have a return type, which is an object class, and it always has an error code in it, and then it has a real result in it. Okay, so that's basically a way to develop multiple return values. Okay, some languages actually allow you to return multiple values out of a routine, or out of a method, in which case you can use one of those values to be your error code and the other one to be the actual value, return value that you want. Okay, so that's another legitimate approach, is to return some kind of compound data structure that has multiple pieces of data, one of which is your error code, the rest of which are the stuff you really want. Okay.
Isn't the array ants only scoped within the procedure or within the object bracket?
The variable ant certainly is.
How would we access that? Because
Well,
you're saying the bracket root only returns an integer,
right,
And so,
right.
but the value of our result will be within that
Exactly.
array ant,
But
which is only scoped within bracket root.
the thing that is scoped within bracket root is the variable ants. And the variable ants is a reference variable. It's actually a pointer off to an array that's out in memory. And although the pointer to that variable might go away, the actual memory that the array, okay, so we have ants points to something here, and here's our answer 3, and the guy who calls it my array also has a pointer to that guy. So when this guy goes out of scope, all that really happens is that reference goes away.
Why does my array have a pointer to it?
Oh, because
Locally within bracket root, does it just get garbage collected when?
if I had called this in the following way, I would do my array equals new int 1. Okay, this is in my main routine. I do this. Then I call bracket root of 3, 4, 10 to the minus 8th, comma, my array. All right, so I've created this array here, which the new makes this data structure out in memory. All right, I've assigned it to, this probably isn't quite good syntax, sorry. Int, so I've assigned it to this variable my array.
There should be doubles there. There should be doubles.
Okay, doubles, sorry. Excuse me for, I'm going to abbreviate double as DBL, but it's really the word double. So I create an array of doubles, which gives me this thing out in memory, and the my array pointer to it. Okay. Now when I call bracket root, it gets passed by essentially the value. It gets passed by value, and the value being the thing here. Okay. So what this guy actually sees is a variable ANS, which is pointing to that. He then does this, which overwrites this thing to be its value. Then it's true that this guy goes out of scope, and this guy goes away. But the thing in memory is, it's better. If you do have a language that allows you to return structured data, it might look nicer to do it that way than this way. Having, like I say, spent several months doing it this way, I find it a nuisance, but it's probably really a nuisance no matter how you do it. The problem being you've just got to put checks for the errors. Every time you do anything, you first see if it worked. Okay? This is especially critical if these libraries are calling some external piece of hardware or something that interfaces to the outside world, because as soon as you talk to something that's not memory, the number of things that can go wrong really goes up enormously. So everything we've talked about so far applies naturally to Java as well. You can do all the techniques that we use in Java. And there's one additional technique which is implemented in Java and is also implemented in many other programming systems. It's called throwing exceptions, and it is pretty much the standard way, or a standard mechanism that you'll find in lots of different languages. It's found in C++, Java. There's special mechanism to make it work in raw C on Windows. As far as I know, there's no way to make it work in raw C on Unix. Raw C on Unix has a much weaker error handling system, and you pretty much have to fall back on this mechanism. And since we were, in my project, using a lot of raw C interfaces, we had to fall back on this.
ANSI C doesn't have that in it?
I do not believe it does. I could be wrong, but Windows has to put special compiler extensions into their system to make it work. Windows actually does a very decent job of this, but yes, go ahead.
Well, just to clarify the difference between the two, then, this one you have that very small percent chance that the two coincide, whereas that one you don't.
Right. This one you always know whether it's success or failure, and you get the answer from here. This one, if you return like negative 10,000 as the error code, if you happen to have something with a root at negative 10,000, bad things will happen.
And the thing is, neither gets around the if.
Right, neither gets around the error checking part, or the checking part. The thing we're about to discuss does get around the error checking part. It lets you write your code as if nothing's going to go wrong, and then deal with anything that could go wrong in kind of isolated places, which is nice. The disadvantage of it is that it's kind of high overhead, so you have to use it sparingly. But it's kind of nice.
What do you mean is high overhead? Processor time, memory time?
Yes, probably all of those things. It means you have to, the system is going to insert extra stuff in your code and insert lots of checks in your code that automatically, but you don't see them in your code, but they'll get executed anyway. Okay, so the basic mechanism of this is known as a throw. This is kind of a very high-level description. Then we'll talk about how to implement it in Java syntax. And the idea of it is that you have some set of nested subroutine calls. Let me draw a stack picture. Here's the stack frame and variables for the first method call, which calls another method call. I'm assuming you're familiar with stack pictures from Scheme or the architecture course. So we're way down here, and we get an error. All right. What a throw basically does is unwind the stack upwards and upwards until it finds, and looking for somebody that says, kind of advertising at each step, I've found this error. Do you know what to do with it? And if it doesn't, it goes up and basically pops the stack, returns everything, or returns as if you had done a return. It cleans up everything, and it keeps looking for somebody who can handle this. When it finally finds them, it stops and executes this handling code. Okay, that's the basic idea. The syntax for doing that in Java is, of course, object-oriented. Exceptions in Java are classed into are objects representing what kind of exception it is. And they are classed in a hierarchy, which maybe I'll draw over here. And those of you who have the book can check to see if I've got it right. The top of the hierarchy is something called throwable, which is just something very high level, and that splits into errors. And these are actual objects and exceptions. And errors correspond pretty much to this sort of thing. Things that if they happen, you're pretty screwed. And so you don't really have to worry about them too much. This exceptions further splits into runtime exception. I'm not sure I have the capitalization right. And I/O exception. Runtime exceptions correspond to this class of thing, which are basically programming errors and should never happen. So that gives us the remaining things. Actually, you're certainly allowed to inherit. I'm going to fix my arrows to make a legitimate inheritance diagram. Forgive me. I/O exceptions, or anything that's not a runtime exception, corresponds to things like this, okay? Unexpected input or I/O error or something that you're going to have to deal with in your program, all right? So if we want to use this mechanism to fix our bracket root problem, we have to do a couple things. We maybe, rather than just using a generic exception, we want to make our own version, which is a bracket exception. So, running out of board. We need to subclass class and I'm just going to call it bracket except rather than bracket exception. And this extends, say we want to extend I/O exception. And we don't really do much in here. We just provide two constructors. One of which is just a null constructor. And one of which, actually, in this we probably in all cases want to call our super. One of which takes a string which says something about what went wrong. And again, all it does is pass that up to your super I/O exception, which knows what to do with this error, which will probably be to print it on the console or in a log file or someplace we know we went wrong. So this makes a new class, which is a bracket exception, which is a subclass of I/O exception, and we've just made two constructors. It has no data in it, it has no interesting routines in it. Really, the only reason we're doing this is to make a new type that we can then branch on or test for later on. The system will test for later on. All right, all is well. Now, how do we tell the rest of the world that something went wrong in here? How do we throw an exception? Well, that's easy. We just use the keyword throw. Okay, if something goes wrong, we throw, and the argument to throw is one of those guys. These parentheses are unnecessary. It's like return. It's whatever value follows is the thing thrown. I like to use parentheses, but that's just me. And we have to make something to throw. We need to throw an instance, so we have to make a bracket except. All right. This is the standard line of code to throw an exception in Java. All right? Now, in many languages, you could just get away with a mechanism like this, but Java wants to do compile time checking to make sure the errors, any error that's being thrown is being handled someplace. So it makes you warn the compiler that you're going to do something like this inside. You would think it would just be able to grovel around inside, see that you do it, but it doesn't. So you have to add an extra warning out here on your method. This is the first kind of extended keyword we've seen on method. Throws, and the thing it throws is bracket accept.
Do you need params after your bracket accept constructor there? You call new?
Yes, thank you.
Also, does that mean each method can only throw one kind of exception?
I think you're allowed to have multiple things here separated by commas. Or if all of the exceptions are in a common hierarchy, you could probably put the superclass there, and it would all work too. Yeah, that would be a bit high, but yeah, maybe throws IO exception or something. So this is the only new syntax here. All right, now what do we do with this thing? I have my main up here, which I had filled in with miscellaneous stuff, which I'm now going to recover. So here's my main routine, and I have a call to bracket root. Okay, but now bracket root has signaled that something can go wrong. It can throw this exception, and the compiler is now not going to let you get away with that. It's going to say, you've thrown an exception here, you got to do something with it. And the way to signal that you're going to process, there's two things you can do when you call something that's going to throw an exception. You can either punt and throw it back to the person who called you. All right, we'll talk about that in a second. Or if you're main, the buck stops here. If you throw an exception out of main, the program will die and print something out. So you, for good form, would really want to do something about this. And the thing you would want to do about it is the way you specify error handlers, catch handlers for exceptions that are thrown are using the keywords try and catch. Okay? Try is kind of a warning keyword. You wrap things in a try block. So anything that throws an exception, that could fail. Anything that throws an exception that you want to handle at this point, you wrap in one of these try blocks. All right? All try does is signal, I know something's going to go wrong here, so be aware. And then you follow the try block with one or more catch blocks. And catch has two parts. It has a type, an argument, which is the type of exception this particular code is going to catch, which is basically our whole reason for doing this subtyping, so we can do this kind of branch here. And say we had another type we defined, other exception. All right. So what this does is it runs the code in the try block. Okay, runs all of it. If it succeeds without throwing an error, if no error has gotten thrown, it's basically going to go from here and jump over all of the catch blocks and keep going happy, happy. Okay, if an exception is thrown here, the system is going to check each one of your catch blocks for the type of the exception. Okay, if you throw bracket exception, this catch block is going to catch bracket exception. It's going to bind the particular exception that you made down here to this variable e, so you could query it for various things. There are, I think, some various methods on Throwable that you could use to query stuff. But basically, here you put code to handle error. Okay, this is where you say, okay, I've got this exception. What do I do with it? How do I fix it up? You put the code in here. When this catch code finishes running, and it can do one of a couple things, it can either throw another exception, in which case the whole process returns. It can do some kind of return. But if it doesn't do that, if it just, execution gets to here, again, it just jumps over the rest of the catch blocks and begins and continues executing. Yeah.
So when we reach an exception and we unroll the stack back to where we find a catch block or something to handle
Right.
the error, does that mean that all the work that we've done on the stack up to that point is
All gone.
Okay.
Yep, all of those stack variables go out of scope. Anything that you've allocated out there that you still have references to higher up will still be around, but anything that you just created new down there and never passed back up, all that's gone. The whole stack is cleaned up for you, which is good if you have a lot of stuff that you've created which is bad. It'll clean it all up for you on the way up, and you don't have to do that.
So there's no way when you throw, you kind of pass back any variables.
Well, one thing you could do, since you do get this exception thing, you could add some data to this, maybe for your particular exception, and start to fill in, fill in some data, carry some data along with this. And then in your constructor here, you could pass back the information that you wanted. Okay, and then in here, since you have access to the thing you threw, you could deal with it. The only thing that gets carried, I guess it's fair to say, the only thing that gets carried up this chain is that exception object which you created.
So we could put integers or strings.
Yeah, you could put a bunch of stuff in there and pass it up and then use it.
And so if you wanted to decide for some reason that if they're the same sign, then A really wanted to be the opposite sign than I was given, and I don't want to communicate anything to the user, I just want to deal with that, you would put that in your exception and then call bracket root again from your catch routine.
Right, if you wanted to decide that at this level, yeah, you would, right, you could just change the sign, handle it, call bracket root again. What you might even want to do in that case is just fix the argument here and wrap the whole thing in some kind of loop, so you only have that call to bracket root centralized up here, okay? Because otherwise, remember, you fix that error, you would have to do another try block in here just in case something else went wrong. So it's best to kind of clean up in your catch blocks and then come around and do the thing again in your try. There's one more keyword which you can put in here called finally. You can put at the very end of your sequence of catch blocks. And that is just a convenience thing, a convenient place to put code that you want to execute regardless of whether the thing throws an error or not. Okay? For example, if there's some code at the bottom of this loop and code at the bottom of this loop which is identical, the bottom of each one of these things that always has to be done, whether the thing finishes correctly or not, you can put it in a finally loop, or a finally handler down here. I guess you could also put it at the end of the catch blocks as well. Move it out there. Any more questions on throw and catch?
Yeah, on the case where we wanted to return some values with the throw, throw back the bracket root exception.
Right.
I'm looking in your code of where you actually throw it, and it just says throw new bracket
Right.
exception. It doesn't really look like there's any place
Right.
you can actually
Well, what you'd have,
save those variables.
what you would do is, first of all, you would define bracket root to say have int, you know, error code or whatever.
The bracket root exception. I mean,
Excuse me?
The way you throw it, you're throwing it bracket root with no parameter.
Exactly.
Bracket exception with
So
no
you would have to add an additional constructor, which would fill in all of the values that you had, and then when you called new here, you would have to fill in those values in the constructor. Okay. So basically, the normal way you would construct an object with data, okay, you would just declare it having instance variables. You would then initialize all those variables in the constructor, and then you could get them out using accessors. Okay, that's how you do that. One more feature of this, say you have an intermediate routine, say main, instead of calling bracket root, calls call bracket, which then calls bracket root. All right. So, but say you still wanted to handle the error up in main. So basically, the stack is going to look like main, then call bracket, then bracket root, and the error, the exception, is going to have to propagate through here. In many systems, you don't have to do anything. In Java, you have to signal that Java is going to complain. It's going to say, you can get an exception out of bracket root. What are you going to do with it? You don't have any try loops here. What do you want to do with it? And so you have to re-add your throws keyword. Okay, to the end of this. So all this says is that, yes, I know I can get a bracket exception from here, and all I'm going to do is keep throwing it up the stack. I'm not going to handle it, just keep throwing it up the stack. So
You don't have to write anything to explicitly do that?
nope, all you have to do is signal this, and the compiler knows that just pass it up. Catch throw is a very generally used paradigm pretty much everywhere. The final issue is, okay, we've got our error. What can we do about it? And for here, there's really not much to say, since it's very circumstance dependent. What you basically want to do is perhaps make the user or some operator aware that the error occurred. Or you can make some decision that this error occurred, and maybe you can fix things up and keep going. Maybe make the assumption that you had the wrong value for A, or had the wrong function or something, and keep going. Or if you can't, if you try to, for example, if the user sent you a file that doesn't exist and told you to read from that file, all you can really do is print out a error message saying, file doesn't exist, and then exit. Or you could, if you got the wrong number of arguments, you could print out a little usage line and a little help text to tell the user what the arguments actually are supposed to be. That's a very common practice and very useful, so that you can just type something bogus at a program and it'll come back with what you should have typed. That's for kind of standalone programs. If you're writing kind of back-end server programs that are serving many different users, you have a slightly more complicated error situation, since you really don't want to crash the whole system just because one user's gave you bad input. What you might want to do is just shut down the user session and then keep going. So, for example, if you're running Java as in servlet mode, okay, if you're running a servlet engine and you call a servlet, okay, a servlet is essentially a piece of Java code that runs inside a web server, and you access it through a normal URL, which causes a method call on a class to be called. If that bombs, okay, you would like only that class and that method and the data structure associated with that particular user to kind of die, and his whole session might die, but everybody else can keep going. So error handling gets much more complicated when you're talking about building a server that can possibly have multiple things going on. You would like very much for an error on one part of the system to not require you to shut down the whole thing and come back up. Analogous, but of course in a whole different scope, is processes and things on an operating system or on the network. You don't want one person or one process causing an error to bring down the whole system, which it used to happen on older systems. You know, anything that went wrong anywhere, everything dies. So we haven't really talked about how to run multi-user server systems yet. So that's really just looking ahead to you know, sometime in the future, if you're stuck doing that, to plant that seed in your mind. Most of the time, if you're writing programs that talk to the console, you would just want to print out an error message and return. Let's see. I guess that's all I want to talk about today. Any more questions on this? Well, in that case, you're off early.